Hello boys and girls. This is Professor Nelson from Electronics. Today we are going to talk about the operational amplifier. This is an operational amplifier, or rather this is its symbol. The symbol of the operational amplifier presents the following elements. The first is its power supply, positive and minus VCC, or GND, that is, negative. The minus VCC means that it works with a symmetrical source, and when it says GND, it means that it can work with normal sources. What is the difference between a symmetrical source and a normal source? This is a normal source, the one we almost always use in projects. In it we have a regulator that gives us positive and GND or negative. That is to say, the operational amplifier can work with a simple or normal source. However, it can also work with symmetrical sources. The symmetrical thing means that it has a regulator to give us positive with respect to GND or a midpoint, and a regulator to give us minus VCC with respect to a midpoint. This is like having an alternating signal. It has a positive signal and a negative signal. So the operational amplifier can work with this type of power supply, which is not very common. Therefore, we are not going to work with this type of power supply, but with a normal or simple power supply. Second, we already know about its power supply. The power supply ranges will depend a lot on the package or the integrated circuit that we are using. They can be powered with only 5 volts, 12 volts, or even 24 volts. That will depend on the model. After that, we have 2 inputs: the positive input and the negative input, and an output. An operational amplifier can work in 2 general ways: as a signal amplifier or as a comparator. So let's see what a signal amplifier is and what a comparator is. Before continuing, let's look at the packages, that is, how operational amplifiers are presented. First, you can find them in 8-pin packages, 4 per side, as is the case of the LM741 amplifier, which is the most common model, but I don't use it much. Since the 741 is widely used by students, it has a drawback. It is that it only has 1 operational amplifier in its package. However, there are other models such as the LM358 that has 2 operational amplifiers internally. So it occupies all the pins of the 8-pin package. So we can have 1 operational amplifier in this type of package, or 2 operational amplifiers in the same package. And we can even have much more. Here I have an LM324, which has 4 operational amplifiers. As you can see here we have 4 operational amplifiers. So this one here is quite used. Now I would like to know in the comments if anyone has been able to find any encapsulation that has more amplifiers in their work or in their studies. Maybe searching on the internet they will find it, but mostly I am referring to work. I mostly find the LM324, the 358, and sometimes the 741, and some other models, but only 2 operational amplifiers in 1 encapsulation. Therefore, we have several operational amplifiers in different encapsulations. Now we are going to work with the 358. We are not going to use the 741 since it is quite old, so we will not use it on this occasion. Well, now let's continue explaining everything about the operational amplifier. Now the operational amplifier as a comparator needs 2 signals in its inputs. As we see here, we have a positive input, also called a non-inverting input, and a negative input, or called an inverting input. in which we have two potentiometers connected. The potentiometers will allow us to vary the voltage levels assigned to both the non-inverting pin and the inverting pin. Therefore, with the knob we will increase or reduce the voltage that falls on any of the operational input pins. As an example, in the case that pin 3 had 1 volt, and in pin 2 we had 5 volts. In this case, the voltage in pin 2, which is the inverter, would be greater than the voltage of the non-inverting pin. Since it is greater, what the operational output will be what corresponds to its sign or its negative input in this case. The operational amplifier would give us less VCC if it had that supply of less VCC. In this case, it will give us 0 volts. By giving us 0 volts, because potentiometer 2 gives us a higher voltage, it will make LED 2 turn on. However, if we make potentiometer 1 increase and go from 5 volts to 6 volts, then the non-inverting input will have a higher voltage. Therefore, the output will be positive, because it has more voltage than the inverting input. By giving us a positive voltage, D1 will turn on because it needs a positive voltage. So a comparator does that. It compares the voltages or tension levels at its inputs. According to that, it will give us a positive or negative voltage. It works as a comparator that's simple. Well, let's move on to the other configuration. The operational amplifier as a signal amplifier. As its name indicates, what it will do is amplify small amplitude signals to values that are necessary or required. I can have a 1 volt signal and amplify it 5 times, 10 times, or 100 times. That will depend on the external components of the amplifier. In essence, an operational amplifier can amplify up to 100,000 times according to the data sheet. That is, if they have 1 millivolt, they can amplify it 100,000 times, and that will be a fairly large value. But it never reaches those extreme values, maybe about 1,000 times or 100 times. Usually a value less than the maximum. Therefore, what the amplifier will do is preserve the shape of the signal by amplifying it at higher voltage levels. The same is how transistors work as audio amplifiers. In order for the operational amplifier to work as a signal amplifier, it needs a relationship between its components. In this case, the resistors that we are going to place in the circuit are on R2 and R1. Since it presents a formula which has 2 general configurations, as an inverting amplifier and as a non-inverting amplifier. Both work, but it depends on which one to use. Or depending on the circuit, one or the other will be used. Since the outputs themselves will not vary much because the formulas are very similar. But the important thing is to have a resistor. As you can see here, a low-value resistor and a very high-value resistor. This relationship between R2 and R1 will give us the factor or the multiple by which our signal will be multiplied. For example, if I put 10 kilo ohms here, and here I put 1 kilo ohm, 10 divided by 1 will give me 10. That means that the signal that comes in here will be multiplied by 10. If it is 1 volt here at the output, I will have in this case 10 volts. The bad thing is that I will have it inverted, because here you can see the sign. It says that it will be minus. So if I put a volt and the output is minus 10, I will not have an output voltage, unless I have a symmetrical source. But if I have a simple source instead of minus 10, I will have GND. So depending on the situation, you can use inverting or non-inverting. Let's look at the non-inverting. The inverting is simpler. But let's look at the non-inverting. The amplifier is non-inverting. As non-inverting means that the signal will have to enter through the non-inverting input. And in this case, the inverting input will maintain the relationship between R2 and R1. So here there will have to be two resistors that allow us to have a relationship, which will be the multiplier, multiplied by the input voltage, but plus 1. But the important thing is that it is positive. So our signal will come out correctly. So we are going to use this more than anything because we do not have a symmetrical source. So the simple source will use this circuit. And as you can see, it goes negative. So the important thing here is to find the right relationship and not go overboard in amplification. We are going to introduce a low-value signal, and we're going to amplify it by a factor of 5, 10, or 100, whatever is necessary. Now, the normal thing when you have low amplitude voltage signals is to have a resistor that limits them, or that prevents that signal from being reduced too much due to the consumption of its current. For example, when you put a battery or a 1.5 volt cell and short circuit the ends, it quickly loses voltage. Why? Because the resistance between the ends reaches zero and the energy is consumed and voltage is lost. The same can happen here. Therefore, we put a resistance of 1 kilo ohm or 10 kilo ohms, unless the signal already has that resistance. Good, now let's move on to practice. Very good, now the amplifier as a comparator. Here we have the circuit assembled as seen in the diagram. We have two LEDs, the operational amplifier, the potentiometers, and I put 2 voltmeters exactly on pins 2 and 3 to be able to observe the changes in voltage levels with the potentiometers. And so we will see at what moment one or the other LED turns on. Okay, here we have the circuit working and with the voltages of each potentiometer. This potentiometer has 3.43 and this other one has 3.8 volts. Therefore, the blue voltmeter LED would be the green one. So it lights up. However, if I increase the voltage of this potentiometer or the red voltmeter, for example, there, the red one turns on because it has 3.8, which is greater than 3.7. If I increase the other one, the green one turns on. If I increase the other one, and so on. You see, a comparator works like this, comparing the voltages of its pins, both 2 and 3, and depending on the result at the output, we will have negative or positive, which will make one or the other LED turn on. There. And there. On this occasion, the operational amplifiers are working at 12 volts as indicated by the circuit. Well, now let's see how it works as a signal amplifier. Well guys, now to see the operational amplifier as a signal amplifier, we put together the circuit as a non-inverting one, as we had it a moment ago, but with certain modifications. The circuit itself would look like this. There you have it, and you can put it together. This here is what I have put together on the breadboard. The reasons right away I'll explain. The first thing you have to see is that the signal we are going to amplify is the yellow one, which has a peak-to-peak voltage of 529 millivolts, or half a volt peak-to-peak. But if you look closely, it is with reference to this point here, to the yellow one, right on the horizontal center line. This means that it is within a continuous component. In other words, this yellow signal is not alternating, but it is within the continuous range, and the signal that we are going to amplify is oscillating there. Now, because of that, this circuit is built. This circuit allows us to reduce that. That is to say, I don't have a pure alternating signal, as it should be. Like this one here, where we have a positive and negative midpoint. We don't have this type of signal from the generator that I have. Since the generator that I have, what it does is give us a sinusoidal voltage, but within direct current. We have 0 volts and VCC. And from the midpoint, it is oscillating. Therefore, this signal is not alternating. So what I have to do is first reduce this midpoint, lower it as much as possible to 0 volts, so that this signal is like this signal. In that way, so what we do is lower it from the middle to as close as possible so that the valley of the signal reaches 0 volts. So that when amplifying it, the signal is much better. And how do we do that? Well, using a voltage divider. Here we have a 20 kilo ohm resistor compared to a 470 ohm resistor. So the voltage between negative and R11 will be quite small, less than 1 volt. We do that in the operational amplifier, that is, at the input. What you are observing is here. Here we are measuring with the oscilloscope. And not here. Now we use this capacitor in this case to obtain the alternating voltage, but within the continuous range. So we are using it to couple the signal. We are going to couple it through the capacitor exactly at this voltage. Imagine that here I have 1 volt, and we have the signal of half a volt. So it will increase and decrease from the reference or midpoint of a volt. From there it will go up and down. That way I can amplify it with the op amp, so that my signal is amplified. Let me just wait a moment. The signal is being amplified by a factor of 10 because of the values I put in. Here I have 100 kilo ohms, and I have 10 kilo ohms that gives me a factor of 10. So as I am delivering 500 millivolts on my output here, you can see that I have 5.6 volts. I am working with a 12-volt source, so I could still amplify until I get almost to the extremes. From 0 volts or negative to 12 volts or positive. I never have to get close, but I do get slightly close so that the peaks and valleys of the signal are not clipped. Well, this is how the op amp works as a signal amplifier. Well, guys, to finish, remember that you will find the op amps on different electronic boards and sensors. They are there precisely to be able to do either the comparison or the amplification of the signals. In this case, I have them here in these small modules. Now, if you liked the video and it was helpful to you, a like helps the channel a lot. See you in the next video. Bye-bye.